I'm going to bring up Brian Bad Mathiesen, and he's professor in energy planning, renewable energy systems at Aalborg University, PhD in fuel cells and electrolyzers and future energy systems. More importantly, he got that in 2008, and that's about when I met. I think he had just gotten that, and he was a starting professor at Aalborg. And he's actually a good friend of mine. We kind of did part of our journeys together. We've met numerous times in Denmark to do short courses on energy and planning. And he's a great guy. I was actually able to talk with him this summer. And when he told me what he was doing with Europe and with the energy roadmap there, I thought he would be a great speaker, because he's really looking at really big systems and electrification and decarbonization systems like that. His research focused on technical and socioeconomic transition to renewable energy storage, large-scale renewable energy integration, and the design of 100% renewable energy systems. I won't go over how many publications he has because it embarrasses me compared to me, but he's done great work. He's published lots of reports, lots of very highly cited journals. I think he's in the top 1% of
general switch here, which I see sold.
What was that? I'm sorry. Oh, and recently he started an Elsevier journal, Smart Energy. In addition, he's a member of the Danish Academy of Technical Sciences and the Danish Energy Technology Development Demonstration Program. He's a deputy chair of the advisory board of the CIP Foundation. I could go on and on. He's also a great guy, and he has an awesome perspective on kind of decarbonization and energy. So with that, Brian, I would like to bring you on. He's going to talk till about 9:45, and then we're going to have about 10 minutes of questions. So just, you can put your questions in the chat, and then at the end, we will go through them and do as many as we can with Brian. So Brian, take it away.
Yeah, thank you very much, Kurt, for those nice words. I'm just going to try and share my screen here, and let me see. If I can figure this out. Does this seem to work?
You got it, Brian. Take it away.
Okay. So thank you, Kurt, for that nice introduction. I think we should get right to it. There's really a lot of details that I want to tell you about. You might miss some of it, and maybe you could ask Kurt or Brianna for the slides afterwards. I'm going to tell you about a smart energy systems perspective on a carbon neutral society. We recently completed a big study of Europe called Synergies, and you can go to our website already and look at all of the material, but I'm going to try and go through what this is actually about. And I know that most of you work on a plant level or a smaller community level, campus level, but some of the principles that I'm working on are really applicable on all levels. See, yeah. So the concept that we look at in my research is called smart energy systems. And smart energy systems means that we use all of the energy carriers to create a much more flexible and robust system. Mainly, probably the electricity grid and the gas grid, but we also work quite a lot with the thermal grid and district energy in order to create more options for energy storage. And by looking at this in a more holistic perspective, we're able to find synergies across the system. And I'll just try and show you here one example that may illuminate what this is about. If we look at a renewable energy system, all of us know that we have to have some kind of storage. And there's a huge difference between electricity storage and thermal storage. If you have a cheap electricity storage, it could be, well, right now the euros is the same as the dollar, so you can relate to it. So it's 125 dollars per kilowatt hour in a pit electricity storage on a hill. But if you have a really large thermal storage, it can actually be $1 per kilowatt hour. So that's one thing. So there's a factor of 100 between storing electricity and storing heat. And then there's the other principle, which is that bigger is actually better and cheaper. Here we see a Tesla Powerwall is maybe $300 per kilowatt hour, whereas a thermal storage in a household, 200 liters, would be $90 per kilowatt hour. So these principles tell us that thermal is much cheaper than electricity. And if you put it into a diagram, which is done here, you can see the efficiency of storages and the cost of storages. And what we see is that thermal storage is 100 times cheaper than electricity storage. Gas storage is maybe 20 to 50 times cheaper than electricity storage, and liquid fuel storage is 2 to 5 times cheaper than gas storage. And when we talk about gases and liquid fuels here, we're over in a power-to-X world, electrofuel world, where we want to create some sustainable fuels for ships and aviation. So that's one thing. And also then there's the efficiency. If you have a battery, for example, or a pit storage for electricity where you want to get the electricity back as electricity, then there'll be a round-trip loss. And by all means, you want to avoid round-trip losses if you can use the electricity directly. Some may say that, well, we cannot store in thermal energy and get electricity, but that's not the idea. The idea is we store thermal energy in order to have a shower, which we're going to do also in the future, or to heat a house. Batteries we need, by all means we need them, but then, for example, we store electricity in our electric cars or electric trucks, and then we wait with using it until it's relevant for us to use. We don't try to put the electricity back on the grid, because this creates all of these round-trip losses. So this is part of the smart energy system. Another part is actually energy efficiency. And here we had this project called Synergies, where we set up a modeling approach. We looked at buildings, transport, industry, energy grids, and we tried to do systems modeling and spatial analysis. And actually what we did was we created bottom-up models for all of these sectors in order to have a very deep understanding of what is actually possible. For example, in an industry, you actually really need to know what is in that black box of industry. What are the temperature level? Do they need steam? Do they need really high temperatures? Is it a steel manufacturer? Or can we replace some of it with district heating? Can we replace some of it with direct electrification or a heat pump? Where do we need to use biogas? Where do we need to use hydrogen? And the same for transport. So what we tried to do is we looked at all of these countries, and we modeled them hour by hour with the bottom-up knowledge of buildings, transport, industry, and the grids in each country. And in order to do so, we have used this energy system analysis tool, which is a free tool you can download, called Energy Plane, where we can look at hour by hour all of the system, and we can get out results on renewable energy capacities needed, the level of exchange with surrounding countries, biomass consumption, balancing needs in the energy storage side, and also the overall sort of socioeconomic costs of such systems. We have then in this Synergies project tried to identify means to actually decarbonize Europe, and we have done so by looking first at each country and then combined the countries afterwards. And when we did that, we compare this with the EU Commission's visions of Europe, and they have also made some climate neutral scenarios, and one of those is called 1.5 tech. So 1.5 refers to the Paris Agreement, and tech means that it has a technological fixed focus, you could say. This system includes somewhat still fossil fuels, it has CCS, it has a bit of nuclear, It also has really a lot of energy savings, a lot of hydrogen, a lot of electrification. And what you see on this diagram here is the 2015 system and the primary energy demand of 18 petawatt hours, and then a future system where there's 13 petawatt hours used. On the final energy side, we see that today we use 13 petawatt hours, and in a future, the Commission has modeled its 8 petawatt hours. So that means that the difference between the 13 and the 8 in a 2050 system is actually the losses we have. We want to minimize the losses because these are conversion. For example, one conversion loss could be that we create hydrogen with electricity, and here we have a loss of around 30-35% in just creating the hydrogen. Anyway, when we do this, we're then able to assess this, and what we try to create is a new vision called SEE 1.5, and then we have a 2030 vision. SEE refers to synergies. Here then the results of our modeling, and I'll come a bit back into the details. So on the far right there, you see the 1.5 tech, the 13 primary energy, and the 8 in the final energy demand. And then you see the synergies vision that we have created using bottom-up knowledge of each sector in each country. And here you see we actually still have the same demand, end final demand, as the Commission has. However, we have really reduced the losses, which means that our input of renewable energy or primary energy is really quite significantly lower. It's 10 petawatt hours instead of 13 petawatt hours. If we look at what the mix is, before I go into further details, we can see that in the 1.5 tech scenario from the Commission, you can see on the top here, you still have fossil fuels, you still have nuclear, and then you have biomass and renewable, the yellow one. In our vision, you see we have slightly more wind and solar, 7 petawatt hours, and then we have the same amount of bioenergy, but we're actually able to exclude the nuclear and fossil fuels. If we have nuclear, we can fit it in, it's not a problem, but we have modeled a system where we're able to do it without. Some of you may wonder, so all of this bioenergy, can we use that? And actually, there's quite a lot of bioenergy available that is sustainable. We don't have time to go into all of that, but we have taken quite good care of looking at what is wasted bioenergy that has no climate effect. And this is typically local resources. It can be manure from agriculture that can create biogas. It can also be sewage. It can also be waste. Some of the waste that we cannot recycle, we can use. It can be straw from agriculture. It can be waste wood from forestry and similar. And when we look at that, we can see that for each in all of Europe, we're able to actually create a good balance. But we also see that some countries have less bioenergy than they need. For example, in the middle here, the large one, we see Germany. You can see the potential in Germany is 400 terawatt hours, but actually they need maybe 640 petawatt hours. Luckily, then other European countries actually have a larger potential than they need. So there'll be some kind of trade on this side. Then you're probably wondering about the costs, and costs are really connected to efficiency. A lot of times, and the more efficient system and the more integrated system you have, the cheaper the system. And what you see here is the 1.5 tech scenario and a baseline that they have from the Commission side. And then you see on the far right, the scenario that we have created using our hour-by-hour bottom-up modeling. And we are able to actually create a system that is around 15% less costly than 1.5 tech. And this is really largely connected with the heating sector, because a lot of times what we see is that heating is treated in a way where we maximize the savings in the household. And what the Commission has done in the models that they have used is that they have actually reduced it to an amount that is both economically unviable, but also technically actually hard to achieve. And what we have done is to create a more balanced system where we are sure we meet quite significant heat savings in the buildings, but then we also integrate the system more and use heat savings. Another key thing that is the difference is that we electrify more things in industry, we electrify more of transport. In the electricity side, we see that we are able to create a system where we have no nuclear, but we still need we do need quite significant amount of renewables, around the same actually as the Commission says. We think we should use more photovoltaics. You might be able to see on the top of the SEE 1.5 compared to the 1.5 tech here on the Commission side. Photovoltaics will be cheaper than the offshore. We still need offshore, but if we can have more onshore wind and more PV, we're actually far better off because it's cheaper and we need to transport it less. On the storage side, which might interest you as well, we have a system here where we more or less have the same amount of hydrogen storage as the Commission, but we have combined it now with thermal storage because we have expanded the use of waste heat and district heating, and we're able to also use some of the electricity in the heating sector much more efficiently. So our storage is bigger and more seasonal compared to the Commission scenario. Just before I move on, I'd like to also point out the scenarios that we build have a very, very high impact on other things than energy. For example, this non-energy impact is the aggregated health cost per sector. And this is really relevant also in an American setting where you will see a lot of local pollution that has actually a large effect on the lives of those that are near those elements that pollute: power plants, boilers in households, transport and industry. Coming back to the bottom-up modeling here, we can see here maybe better the differences. What you see is we have actually a higher energy demand in buildings compared to the 1.5 tech, but around the same final energy demand in industry and transport. If we dig into how we have modeled, we have done quite significant modeling of each country. We have maps and knowledge of the buildings in Europe down to 100 by 100 meters, so on a very small scale. And we can calculate using GIS the cost of district heating grids, actually also electricity grids and other grids, but here's district heating grids. And what we try to do is we make a system analysis where we combine different levels of heat savings with different levels of district heating in order to understand where is the balance on how much we should save energy and how we can sustainably supply energy. And in this case, we see that we have 60% district heating and 40% individual heat with an energy saving of around actually 40% or something like this. Anyway, the heat demand in total, when we look at Europe, is reduced by approximately 40%. And 40% is actually quite a lot. And as I told you before, it's less than the Commission suggests. And to go beyond 40% will be highly problematic because we start to actually want to save quite a lot on the hot water consumption as well in order to meet the targets. And that's actually almost impossible to do. So 40% we believe is a good level. That saves a lot on the cost side. 50% of the heat is supplied by district heating with significant amounts of excess heat as well. and we use around 630 terawatt hours of low temperature waste heat, which is about half of the potential. And we can then also go into different details with each country on how that looks like. But here you see, this is the Commission scenario on the far right, 1.4 petawatt hours, and we have a system where we use 1.9 petawatt hours, and you see the beige one, or what we call it, is much larger in ours. That's the district heating, and actually in the 1.5 tech they have something which is really crazy, hydrogen boilers. So you imagine you put up a wind turbine, you make hydrogen, so you have that loss where you need at least 1.5 kilowatt hours to create 1 kilowatt hour of hydrogen, and then you put it into a boiler to create 40-degree hot water. It's completely crazy, and this is of course something that we completely eliminate because it doesn't really work. And then we have also here quite a lot of natural gas boilers, which is offset by carbon capture and storage, and we simply say we should not continue with natural gas boilers if we can do something else. If we look at the district heat supply, we used waste incineration. If we start here from the right, we have a slight amount of boilers to have a balance. We have combined heat and power. We have small amounts of solar thermal. The solar thermal is great, but it doesn't really fit too well with the heat demand. So that makes it having a limited potential, so to say. Then we have low temperature heat pumps. This is really key, because it means that we can use electricity when we have a lot of wind in the system and create district heating, and we can then store that in the large thermal storages that I told you about before. Then we also have excess heat, and excess heat we have also used our mapping system to localize, to understand where they are currently placed, in order to also assess how much of this we can use. Overall, we can say for each country, what is the heating mix, how much excess heat do we have from the industries in those countries, and as you might expect, there's quite a lot of industrial waste heat in France, Germany, Italy, the UK, but in those countries the heat demand is also really large, of course. When we look at industry, we have created a bottom-up model to look at that. It has really a lot of nodes inside, a lot of data inputs, but what we are able to create is a system where we use more electricity. You see that with the bottom here. We also use slightly more hydrogen because we want to displace all of the natural gas, which has not been done in the Commission suggestions. When you look at transport, we are creating a bottom-up model called transport plane, where we understand the modes of transport, what the transport trips are, how long they are, what the purposes are, in order to understand how much is the potential for technical changes to public transport or to electric vehicles. And what we are able to say is that the type of infrastructure investments we make in transport is really important. If we invest in roads, we're going to have a growth in road transport. If we invest in rail, we're going to have a growth in rail transport. So here are some key choices that have an effect, not now, but on the longer term. We can also see that we're able to electrify much more when we look at it from a more bottom-up perspective, because the trip lengths are really short when you start to look at the human behavior. So then we had quite a lot of a problem with this energy crisis that I guess you all know that we're in, and we're really hit quite hard here in Europe. And this is the president of the EU Commission, Ursula von der Leyen, and there's really been a big focus here. And I would say if we hadn't had the COVID crisis, we would have been in trouble, because the COVID crisis has meant that the European Union is really able to rapidly decide on remedies to let's say to make us more robust against these things. And this has also happened during the last half year, when we had the war on the European continent, that European countries have really stepped together, and the Commission has made some really great policies let's say to deal with this crisis. And we also made some suggestions to this, and what we did was we tried to see our 2050 system, and then we did some backcasting, so to say, in order to understand what measures could we actually front load and decarbonize, and to get rid of the natural gas use. And we then made a suggestion on this, and I won't go too much into that. I think the Commission suggestions are actually rather good, but we have then suggested to have less emphasis on hydrogen and more emphasis also on savings and more structural elements. And these policies are called Repower EU, which is put on top of the EU target of 55% CO2 reductions in 2030. I think with those words, I would like to end, in order to also have some time for questions. So for now, I would just say thank you for the word, and I hope that you understood some of the things we said.
Brian,
Yeah.
thank you so much. And part of the reason that I was interested in having Brian come here is because this is obviously a different thing that a lot of us are dealing with every day, which is the, building by building, but the recognition that it has to fit into a system that is going to end up in some way being sustainable. Obviously, you can't have EVs don't work if we're not producing the electricity sustainably and all these kinds of things. So I like that Brian was able to bring like the big picture to the same work I think that we're all trying to do here. So I'm going to, Brian, just go through a few, and you can just, well, one I think is the elephant in the room. With Russian gas shipments reducing stoppages, what sort of decarbonization investments are being accelerated?
So there's quite a lot being done, and I have maybe a speech every second day about what we're doing on this, and what we're doing. Three things. One thing is we're doing an expansion of our LNG terminals. So we're expanding where we can get natural gas for. Then what we're doing is we're doing fuel shift. And that means that we are actually changing from natural gas to coal or oil as an intermediate solution. And this is not a long-term solution, so there's strict rules that it has to be phased out again. But the main thing that is interesting is that we actually see quite a lot of district heating. We see quite a lot of electrification, that the industries are electrifying. We also see countries are doing heat planning in order to get rid of natural gas boilers. In Denmark, we don't have that many boilers, but we do have some. But in the rest of Europe, I mean, we have maybe 45% of the households that use gas. It's a crazy amount. And there's quite a lot of work done on heat pumps and electrification of these. And there are really two good solutions on the heat side, and that is district heating. When you have, and you can go to our maps actually on the website and see that on synergies.eu, and also individual heat pumps. And I'll just say, this has succeeded to a level that I would not have ever expected. You have to understand that 30% of the consumption in Europe is gas, and 40% of that is imported from Russia in a normal condition. So to change that really fast is very highly problematic. But what we have been able to do is that the gas from Russia has been reduced faster than we thought. But even so, we've been able to fill up the gas storages. And gas storages are something that we need to heat the houses during the winter. So normally we would have the gas storages and then the gas inputs from Russia. But these gas storages are full because the savings are working. Because on top of these structural changes, people are really behaving differently. You're seeing electricity savings to a large extent and natural gas savings to a large extent.
Wow.
I could talk for hours on that, but I won't.
Okay, and then maybe just spend a second on this because I want to move to some of the other ones. And this is just, I think, talking about, is this going to, would there be some inclination to continue with these non-renewables? And it says, are there any indications the rightward shift of European governments will impact the decarbonization efforts and investments? So maybe
no, but there is a really serious problem, and we have to understand that we have a war, which means that the energy prices are so high that people cannot pay their mortgages or their medicine or their food. Yeah. And in this situation, we need to step up and use all the remedies that we can, because the other option is really social chaos and political chaos. But it's not a permanent solution. There has been no backing on renewables. On the contrary, we've seen more renewables, more energy efficiency. So if anything, this is going to accelerate when we can achieve a much higher greenhouse gas reduction.
Okay, and then these are moving to there were a couple questions about storage. One was, what about chemical storage and hydrogen? I think you talked about hydrogen, ammonia, formic acid, other things like that.
So this is, I mean, I didn't talk a lot about power to X. This is a big part of our research actually, but if we look at the heavy duty transport, we see more and more that trucks are actually going to be electrified to a large extent. But we do have ships and aviation, which is problematic. And for ships, ammonia is really a good idea because you don't need the carbon source. But the game is not over. It can also be methanol, so a combination of methanol and ammonia. And from methanol, you can create the jet fuel. But then where are the storages? So when we analyze these things, we can see that it's really necessary to limit the hydrogen storage and expand the storage of nitrogen or the storage of carbon, because those two storages are much more efficient, much cheaper than the hydrogen storage. Hydrogen is cheap to transport, but it's really expensive to store. So we want to store in ammonia, methanol or jet fuel, the final fuel, that's where we want to store, or we want to store nitrogen and carbon. We want to avoid systems where we store hydrogen, because then the final fuel cost will just explode.
Yeah. And then do you consider geo-exchange, closed loop geothermal as thermal storage?
Yeah, it can be, but I haven't seen that it's a very large element on the system level. I would say it can be some local, it could be a local solution to do something like that. But otherwise, what we see is actually like larger pit storage in larger city areas. Maybe you can store for 5-6 hours, which is really quite which analysis show is actually enough in a lot of cases. I don't really see that on the larger scale as a solution, but locally it can.
And I think is in Aalborg where you're using an old a mining lake to for cooling.
They're going to use that. Yeah, they're using it for cooling, but in smaller cities you would have simply a stainless steel metal tank, but you can't have that for larger cities. Here you need a combination of production, and you can also have actually old mines that you fill up with water and make sort of a thermal pit storage. That maybe have hot water for 4-5 days. It's not a seasonal storage, but that's okay. We don't really, when we look at the system level, it's a misunderstanding that we need a lot of seasonal storage. We actually need these intermediate storages. The seasonal storage, you could say, in the future will be the chemicals that we talked about before.
Great. And then somebody asked, what are the percentages in the EU of renewable gas, nuclear, and coal? Just kind of like, I think that's maybe current. In overall, what is the mix, I guess?
So I would say for renewables, I think we have around 25% now, or maybe it's closer to 30. I don't have the numbers completely in my head, but the renewables are exceeding the nuclear on the overall level.
Yeah.
Many countries have, like Denmark, we have 50% wind power, but a lot of countries have 15-20% wind power in the electricity grid. Got it.
Okay, great. Let's see here. We're getting through it. Yeah, it looks. Any other last questions? We're about to transition to the next speaker. Brian, anything you wanted to say that you didn't get in your slide deck?
No, I would like to say that I really hope that you could get something out of my presentation. And I wish you good luck with all of the work you're doing around the world. And please think about using all the energy vectors that can really create quite a lot of synergies. And savings are always a good idea. We didn't talk a lot about the synergies, but if you have a building stock, when you do savings in the building stock, it fits better with district heating because you need lower temperatures. It fits better with heat pumps because you get a better COP. So the synergies of the combined system is really important to try and identify. So
thanks a lot, Brian. And just so everybody knows that I'm doing my part, just like Jimmy Carter said in the 70s, to put on a sweater. I put on my jacket instead of turning on the heat this morning. Anyway, let's, Brianna, you want to move us through here?
Yes, thank you, Brian. It looks like we might have had one more question come in, which is, have you done any studies on using phase change material for the TES media?
No, we have not. But in general, what we see is that if it has similar properties as a battery, it will be better to use the different, let's say, to consider the different end demands and put the storages between the end demand and the renewables. Because if every time we think about putting electricity back to the grid, storing electricity, putting it back on the grid, you have to consider that there can be other options that are cheaper and where this is not compatible. And then there can be some local solutions where it could be, but in general, it can be hard to compete.
Okay. And we are on time, but I think maybe we have one more minute. One more question. What's the current state of using renewables for ammonia production?
So the status is not good at the moment. I would say we have, though, I know a big Danish project where we have one gigawatt electrolysis to produce renewable ammonia, which is expected to start in 2025, mainly for the agricultural sector, not for fuels, but for fertilizing, for fertilizers. And then there are some people here that think, oh, well, we can't do that because the electricity prices are so high at the moment. But this is more complicated than so, because at the same time that these are going to start, there are going to be contracted new wind turbines, which they have bought electricity from. So it can actually still go online, many of them, even though at the moment we have an energy crisis. But let's see. Of course, the energy crisis means a lot for electrolysis and it really is a showstopper for that. On the other hand, it accelerates energy efficiency, electrification, wind and solar quite significantly in my experience.
Great. Well, thank you so much, Brian. I had the pleasure of meeting Brian in Denmark this summer and was very excited to see him speak for real today. So I've seen the energy plan tool and it's very, very neat. So I encourage all of you to take a look at it online.